Lesson 1 is a geometry review, and before we get started with the review, I want to cover a few things, and this will probably be one of the longer lessons in the entire book, but I need you to really pay attention. I'm going to talk about some things that aren't necessarily geometry related, but that are very foundational to the rest of the book and just to my teaching philosophy, what I want to try to get across to you. I have on the screen there, you need to have a protractor. That's what measures angles, right? A ruler, a drawing compass, you know, the thing with the pencil on one end, the point on the other that you can draw circles with. Have one of those, a graphing calculator. I use a TI 83 Plus, and whenever we have problems involving a graphing calculator, that's the example I will use is the TI 83 Plus. And also get you a small spiral notebook as well, like maybe a 5x7 size notebook that you can write formulas in. My background is in science and engineering, and in science and in engineering we use lots of different tools to help us solve problems, and that's a huge part of learning mathematics, is that helps you develop thinking and problem solving skills. So think of the rules, the formulas, definitions that you'll be covering, think of those as tools. And you can write those down in this notebook, and that notebook can be like your toolbox. And anytime you need it, a test, homework, whatever, you can open up your toolbox, find those tools that you need. The most important thing is knowing how to use those tools. Now, I'm not advocating that you don't have to memorize anything. That's great if you memorize every rule, formula, and definition that we cover in this book, but I don't think you have to. I don't think you have to stress yourself out trying to memorize a bunch of different rules, formulas, and definitions. The most important thing is being able to use those to solve a problem. If you had a pair of pliers, you didn't know the clamping end from the handle end, then that would not help you solve a problem if you needed the pliers. The same way in mathematics. If you had a formula that you needed to use, you have it in your book, that's great, but if you don't know how to use it, then that's a real problem. I'll be talking a lot about something called deductive reasoning. It's just a type of thinking process where you start with a rule, a formula, or a definition, and you use that to learn new things or to solve problems, in other words. That's called deductive reasoning. Start with a rule, apply it to learn something new. And I just think it's a really good thing for you to have somewhere where you are keeping a list of all the different rules and formulas and definitions that we cover throughout the year. Well, before we get started with the geometry review in the Saxon textbook on page 1, I'd like to just do a little bit of a historical perspective of geometry. And usually we start talking about the Greeks because the Greeks had a lot to do with developing geometry. But I just want to make a few things a little more clear. Hopefully you watched the Getting Started lesson and you saw that I was a Christian, and I'm going to be coming from a Christian biblical worldview as I teach this course. Like I said, I have an engineering background. John Saxon had an engineering background too, and sometimes engineers are a little more aggressive with their mathematics than some people. They don't take time to look back at the history and everything. They just say, give me the formula, let me go build an F-16 or whatever. I just want to make sure that you know that I know that God is the generator of all knowledge and wisdom. So in our historical perspective, let's just start with the flood. That was about 2400 BC, 2,400 years before Christ. And we'll just call it, I mean, it wasn't Noah who made the flood, but he was the most instrumental person in that event. And what happened there? God told him to build an ark, put 2 of each kind of animal on there. God gave him specific measurements on how to build this ark. He gave him standards. So those are like rules, right? Noah applied those rules to build the ark. That's basically what deductive reasoning is, applying a rule. Now the Greeks are credited with founding the deductive reasoning process. But I mean, if you add the biblical perspective, that cannot be true. I mean, God is the creator of everyone. God knows how we think. So God is really the creator of this thing that we call deductive reasoning. I'm sure God doesn't have that name for it. I guess if anything, God calls it obedience, following His rules. So even though we know God is the generator of all geometry, all forms of logic, all forms of thinking and mathematics, the Greeks wrote a lot of things down, and that's one reason they're credited with the discovery of it. And Thales, around 600 BC, kind of got things started, climaxed with Euclid and his book called The Elements. Basically what he did was summarize all of the geometry work that had been done up to then. And he is kind of the one who is called the father of logic, who's credited with the deductive reasoning process, where you start with a rule, you apply that rule to learn new truths. Now it's interesting that the Greeks had access to the Old Testament at this time, but they rejected its message and they chose to worship themselves and nature instead. For example, they might see some geometry relationship in nature, maybe like a bubble or something, just this perfect spherical shape. And they would look at that and say, "Oh, bubble, how awesome you are," instead of saying, "Oh God, how did you make that bubble? How did you come up with the ability to design something so perfect and just so interesting?" And I think it's interesting that the Greeks' study of mathematics stagnated, and it's probably because they just ended with a worship of themselves and nature, and that's just not as interesting as trying to figure out why God made it the way He did, or how God made it. As a Christian, I think that God has given us geometry as a way to study His creation, to build things that give testimony to His perfection and complexity, and to care for others. We could build a building for somebody, design a pair of glasses that would help somebody see better. There's lots of geometry involved in something like that. You have to get the lens just perfect so that the light bends at the right angles. Just keep those things in mind as we're doing this book. Yes, it's important to know math just so that you can get into college if that's your goal, or to go be an engineer if that's your goal. Most importantly, give thanks to God for making mathematics. He's the creator of it, and He has done this so that we can know Him better, mainly by studying His creation and seeing the different mathematical relationships that are there. Okay, end of my sermon. Let's get started with Lesson 1, Part A, on points, lines, and rays. I'm going to go fairly quickly, mainly just because there's so much to cover here. If you need to go back and read some of the things here, there's lots of rules and definitions in this to read about. Those are things you don't necessarily need explained to you. You just need to know and be aware of them. And it's a review, so hopefully you've seen it before. Think about a point. Draw a point on a piece of paper. A point is zero-dimensional. It doesn't have any direction. It just defines a location. Or does it define a location? Think about that point that I've just drawn. We could magnify that point, right? If you drew that on your paper and you put a magnifying lens over it, you could magnify it. And so now what location is that point defining? It looks a whole lot bigger, right? Are we defining this red dot there, or this one, or this one? We can magnify each of those dots too. And where would they be defining? What location would they be defining? What exact point? What I'm trying to get at here is an exact mathematical point is just an idea in our mind. It's not a reality thing. We can never exactly define the location of something. We can get fairly close, but that should just keep us humble and know that God is the only one who is exactly perfect. If we're building a house on a piece of land and we want the northwest corner of the house at this exact spot, we can't ever get it exactly there. We can get close to that. We can get close to perfection, but we can never get it at the exact point that we want it. A line is the same way. We can draw a line. Usually we designate that with arrows on the end, saying that it continues on forever in both directions. Again, we could magnify that line. Where is its exact location? Well, we can kind of represent where its location is by drawing on the paper, but an exact line, a real mathematical line, is only an idea in our mind. Again, because it goes on forever. I mean, we can't draw a line and just draw it forever. God is perfect. Reality for us is that we are imperfect. We can get close, but not quite. And Euclid, we talked about Euclid a little bit ago. He wrote that book, The Elements, and basically what he did in there was summarize 10 rules, or what he called postulates. Those are statements that can be assumed to be true. You don't have to prove them to be true. And those 10 rules were used as the foundation to learn new rules and new truths about geometry relationships. Notice I just drew 2 points on that line, 2 red points. That's Euclid's first postulate. 2 points determine a unique line. That's what you have to have in order to define a certain line. You have to have at least 2 points. I mean, if you had 1 point, you could draw a whole bunch of lines through that, right? It doesn't define just one line. Well, let's use deductive reasoning. Remember, that's where we apply a rule to learn new things, and talk about Euclid's first postulate here. Apply Euclid's first postulate. 2 points determine a unique straight line. So that means we could name those 2 points, give them a name, point A and point B, and we could define that line. We could name that line. We could call it A, B, and we could put a line symbol over the top of AB, and that's how we can define that line. We could also define it as line BA. It doesn't matter what order we put those in. Now, what if we just wanted to talk about the distance from here to here? That's called a line segment, and we would represent that, AB, with a line segment. We don't put the arrows on the end because that's how we represent a line segment. We could also do it segment BA as well. So that's how we name a line and a line segment. If we just want to talk about the length or the distance from A to B, we would just say AB equals blank inches or centimeters, meters, whatever it happened to be that we used for measuring units. Now look at those 2 line segments that I've drawn, segment CD and EF. They look pretty similar, don't they? I tried to draw them exactly the same length. We could represent that they are the same length by just saying CD equals EF. Remember, we don't put bars over them or anything when we're talking about their lengths. Now, if we want to say that they're congruent to each other, we would say CD is congruent to EF. That's how you draw the congruent symbol, is you put that little wave or tilde mark over the equal sign. Do you remember what congruent means? Congruent means equal shapes. The shapes are identical. In other words, you could lay one on top of the other and they would match up exactly. Did you know that the Greeks didn't use rulers when they were studying geometry? They were just more interested in shapes and what they did. So they really weren't concerned with equal lengths. They were concerned with equal shapes, congruent shapes. Let's talk about the last part of part A here, a ray. A ray, we sometimes call that half a line. It has an end point, so we draw a point, and then we draw basically half a line in some direction. Now, that has to be defined by at least 2 points as well. So we could call this point A and point B, and we would name that AB with a ray over the top. Now, it is important. You can't say ray AB or ray BA. You can't change the letters around on this. And it's probably easy to tell why, because it has one end that's not the same as the other end. Point A is where it starts, so we always write that starting or end point. We always write that first, and then a second point. Now, we could have a third point on here, and we could call that ray AC as well. We could call it ray ABC. We can't call it ray BC though, because we always have to have the endpoint as the first letter. Now watch this. Do I have a line now, or do I have collinear rays? Well, it could be either thing. Collinear rays, we would say that ray AB and ray AD are collinear. They're on the same line. We might also say that ray AB and ray AD are opposite rays. Just a special name for a pair of rays when we're comparing them. Something that you don't use really. I don't think you'll probably ever use that ever, is need to be concerned with two opposite rays like that. Except when you're dealing with 180-degree angles, which we'll get to in a minute. So think about points. Points, those are zero-dimensional. They just define a location. They don't define any direction at all. Lines are one-dimensional. They do define a direction. Let's go on to part B on planes. Planes are two-dimensional. They define two directions. And the best way to think about a plane is like your tabletop or a piece of paper. The piece of paper that you're writing on, remember you're supposed to take notes on everything that I put on the board. So hopefully you are doing that and you're taking notes right now. And all of these geometric shapes, we can never do them to perfection. We have these ideas about what they are, but we can't ever have a perfect plane, because a perfect plane has no thickness to it. And a piece of paper, I mean, it's pretty thin, but it still has a thickness to it. We could magnify the edge of that paper and see that it has a thickness to it. A mathematical plane, though, we can represent its location. And usually what we do is kind of do a perspective drawing, it's called, where you have kind of make it look like it's flat. See, we could add some legs there, make it look like a table. See right there, drawing, when you're trying to draw something realistically, there's an application of geometry every time you do that, because you have to get all these angles right so it looks like you have a three-dimensional shape there, even though you're drawing on a flat surface. But this is an art class. If you want to do a lot of geometry though, you should do art, because that's where you do a lot of it. Planes are flat, two-dimensional surfaces with no thickness to them. We can name them just with one letter. I'll call that plane A. A plane can be determined by three non-collinear points. So that means that those points don't have to all lie, or they cannot all lie on the same line. There's another way you can define the location of a plane as well. That's by two intersecting lines. Two parallel lines as well can define the location of a plane. Two intersecting or two parallel lines, and then also three non-collinear points. Those 3 points that I've drawn there, they can't all lie on the same line. That's why it's called non-collinear. Not, the co means on, not on the same line. We won't be using planes a lot in this book, and like I was saying, if you want to do a lot with geometry, learn art, and planes, that's probably one place that they're used the most, is in realistic artwork, because there might be a lot of different flat surfaces that you want to represent. Now that line that I've just drawn, it's going through the plane, it intersects the plane, but it's not lying on the plane. We call those skew lines. Lines that don't lie on the plane but intersect it, those are called skew lines. Points are zero-dimensional, lines are one-dimensional, and lines are actually, we could think of those as an infinite connection of points. Planes are two-dimensional, and those could also be thought of as an infinite group of points representing that surface. It takes a minimum of 3 points to define the location of the plane. It takes a minimum of 2 intersecting lines to define the location. That's another way. You don't have to have both ways. You can have one or the other. And it takes a minimum of 2 parallel lines to define the location of a plane. You could have an infinite number of parallel lines also, but it just takes a minimum of those things to define its location. Let's move on to angles now, and here's an application of some angles. To draw a drawing like this, you have to think about planes, use those, and use angles. You got to get your angles right to make the road look like it's coming from a long way away up through that pass through the mountains at the top. Looks a whole lot more realistic and a lot better perspective than what I have drawn now, right? With no angles involved there, no perspective. So angles are also two-dimensional, and we can define an angle by 2 rays that have an endpoint in common. Just go ahead and put a point on your paper and then draw one ray coming out. And if you have a protractor, which you should have, go ahead and put your protractor up. What you do is you put the center, if this is the protractor right here, you put the little dot that's in the center of the protractor right over the endpoint, line it up with that ray, and then at 30 degrees, let's make a 30-degree angle, put a dot where the 30 is on your protractor, and then you just draw a line through it. And there's your second ray. And so we have drawn there a 30-degree angle. So we can think about an angle as 2 rays that have a common endpoint. So that endpoint is really important when we want to name an angle. And let's just call this one, remember we have to have 2 points to define a ray as well, so let's put that as A, the endpoint as B, and then put a point on the other ray, call that C. And so we would call this angle ABC. We always put, when we use the 3 letters to name the angle, we always put the vertex or that endpoint as the middle letter, because that's kind of like the cornerstone of it. We can't say angle CAB. That doesn't make any sense. That's just how everybody knows what the vertex or the endpoint, the common endpoint of that angle is we put that one in the middle. So we could also say angle CBA. We could also just use only the endpoint to name it. Call it angle B. So like a plane, we can use one letter to represent that particular angle. When you're dealing with circles, we talk about angles a lot with those as well. And another way to define an angle is the region bounded by or in between 2 radii, as well as the arc. That arc is the edge of the circle, right? So this region right here up to the arc, we could think of that as a way to define an angle too, the region between 2 radii and the arc of a circle, basically the sector of it. Let's draw another 30-degree angle. Put this one right over here. I'll draw one ray first and put its endpoint, and then I'll put my protractor up there, put a dot right on the 30, and then draw a ray through that. And we'll call this one DEF. Okay, now we know that both of those are 30-degree angles that we have on the board now, and so we could say the measure of angle B is equal to the measure of angle E. We put that little M there when we're talking about the measures. Remember, just like when we do lines, we say that one is equal to the other, their lengths are equal. And then we could say, if we want to talk about them being congruent to each other, we would just say angle B is congruent to angle E. Remember, the Greeks, they were not concerned with what the measures of things were. They were just concerned with equal shapes, or congruency. Now when we do measure an angle, usually what we do is we start with the bottom ray and we go up like that, and we'd say that's a 30-degree angle. Now think about a circle. There's 360 degrees in a circle, right? If you went up and around one time, that would be 360 degrees, and then up again to that ending or terminal side. We call the side that we started with the initial, the one we ended with the terminal. We would say that's a 360-degree angle. And I mean, you can do that. That's okay. I'm sorry, that would be a 390-degree angle, not 360. We had that initial side that we started with, ray EF, and then the terminal side. I mean, we could just keep going around and round and round and round. An angle can be like that first one. That's usually the one that we talk about when we define an angle, because it usually doesn't help us to talk about those multiples of 360 that we could also define that angle by. So we could say that's a 30-degree, a 390, a 750-degree angle. We could just keep going and going. Normally when we measure an angle, though, we just start at the initial, stop at the terminal, and get that measurement. Use a protractor to find it. Look at the bottom of the screen. There's 4 special kinds of angles that we talk about a lot, and one of them is a straight angle. That means that here's the end point. We have one ray going this way and one in the opposite direction. A right angle, the rays are perpendicular to each other, and we always represent perpendicular rays or sides on a polygon. We put a little box on the corner there to represent that those are right angles or perpendicular to each other. A right angle's measure is 90 degrees, right? So a straight angle's measure is 180. Let's just write those down. Acute angle, it's less than 90. So we can just put less than 90 degrees as its measure. And I mean, it could be 80, 70, 60, it doesn't matter what it is. It's just less than 90. And then an obtuse angle, you can probably figure that one out. It's greater than 90. So those are 4 that you might want to put in your notebook, your spiral notebook, just to remember those kinds of angles. Let's look at 2 more angle relationships, supplementary and complementary angle. Supplementary, what that means is you're looking at pairs of angles when you're dealing with these 2 things. Let's call this angle X and this angle Y. They would add up to 180 degrees. There's a good rule to put in your notebook. That's how we define supplementary angles. They add up to 100 degrees. Complementary angles are based on 2 angles that add up to 90 degrees. So we'll call that X and Y. X plus Y equals 90 degrees. Put that definition in your notebook as well. Anytime you're dealing with a pair of definitions like that, it's easy to get them confused. So try to memorize one of them, and then by default you remember what the other one is. Supplementary, add up to 180. Remember that one good. Complementary, hopefully by default you remember, oh, that's the one that adds up to 90 then. Part D of this lesson is on betweenness, tick marks, and assumptions. And look at this line here that we have, line X, Z. Let's put a point Y in between. It doesn't have to be exactly in the middle, but that's what we talk about when we think about betweenness. We would say that point Y is between X and Z because they all lie on the same line. Point A that I just drew, we wouldn't say that that's between X and Y because it doesn't lie on that line. So just something to keep in mind. When we're talking about something being in between, we mean that it's on the same line with the other 2 points. Now look at these 2 triangles, and we'll learn about tick marks and assumptions by looking at these. Are these congruent triangles or are they not? How do you know if they are or not? Well, they are congruent, I used a little plastic triangle to draw both of them and try to draw them as exactly as I could, so they should be congruent. But don't ever assume that the two triangles are congruent unless you have some way to prove that. For example, this is a right angle on this corner right here. So that's one way that we can tell that those angles are congruent. If there's that little box on the corner, that tells us that those angles are right angles. And another way is by tick marks like this. If we put a single tick mark there, we use that little arc to designate angle measure. Put one tick mark through this one as well. When we see two angles like that, when we're comparing angles and we see that they both have one tick mark in them, that's telling us that they are congruent to each other. And we use those tick marks. You'll see those in your homework problems as you do them, and they will use those to help you know which angles are the same. So those two that we have on the top there, we put two tick marks through both of those angles to tell that they are congruent as well. We can do the same thing with sides. Put one tick mark on this one tick mark on that one. That tells us that those sides are congruent. Put two tick marks on that one, two on that one, and that tells us that those two sides are congruent. And we could put 3 here and 3 there, and that would tell us that those two sides are congruent to each other. So the whole point here is don't ever assume that angles or sides are the same unless there's some way to prove that. And there's symbols that we use, tick marks, the little perpendicular boxes on the corners, to show congruency. Let's look at part E on triangles, and we can classify triangles based on their angles or based on their sides. There's two main ways to classify them. Based on their angles, we have at the top there an equiangular triangle. See, we have one tick mark for each of those angle measures saying that all of those are equal to each other. Do you remember what they have to be if they're equiangular? Well, remember the sum of the angles in a triangle always adds up to 180 degrees, right? So if they're all the same, that would be 180 divided by 3 is 60 degrees each. Isogonic. See, we have two angles that are the same there. So iso means same. In an isogonic triangle, two of the angles are the same. A right triangle, that's pretty self-explanatory, one 90-degree angle. An acute triangle, that means that, think about that 90 degree in the right triangle, it's just a little bit less now, and so that makes all of the angles less than 90. And obtuse, look at the right triangle as your base one and extend that left side out to the left some, and you get an angle greater than 90. That's an obtuse triangle. One angle greater than 90 degrees in an obtuse triangle. And an acute, all of them are less than 90. So there's a difference there. It's not like you have one less than 90 in an acute. All of them are less than 90. And obtuse, one greater than 90. Now triangles compared, or talking about their sides, classifying them based on their sides, you have an equilateral. That means all sides are the same. An isosceles has two sides the same, and a scalene, you can just look at the tick marks there and tell that you would define that by no sides are the same length. Look at what I have written there at the bottom. That's something very important. You might want to put all these triangle classifications in your spiral notebook that you're making, and that statement at the bottom, the length of a side, and that's for a triangle of course, is related to the angle opposite that side. For example, look at this. If I want to draw this triangle right here, I could put that side like that. Now, think about that same triangle. Let's just make that top side longer. Now that makes the opposite side longer. When we make that angle here, the first one, here was our angle, and that opposite side was shorter. And then we made a bigger angle there on the left side. That made that opposite side bigger. The bigger the angle opposite that side, the longer the side. I mean, those things are related to each other. That's why in an equilateral triangle, all the angles are the same measure in it as well. All the sides are the same length, so that means all the angles must be the same as well. Let's go into part F on transversals. We're almost done here. Hang in there. Focus on what you're doing. If you want to take a little break or something, go ahead and do that. I mean, this is probably the longest lesson in the whole book. But if you get this down good now, it's going to make everything else easier. Let's talk about transversals. When we have two or more parallel lines, let's just do two for right now. Remember, we designate parallel lines. We don't put the arrow at the end. We put it before the end. And that's how we symbolize that those lines are parallel. Don't ever assume lines are parallel unless you see those arrows. A transversal is a line or line segment that cuts through those. It doesn't matter what angle it cuts through them at, but it does pass through two or more parallel lines. That's just what a transversal is. Now look on page 8. There are some properties of parallel lines, or in other words, some rules about parallel lines that we have there that we can use to learn new truths. That's what deductive reasoning is, right? You have some rules that you apply to learn new things. You might want to write those properties down in your spiral notebook that you're making. Look at the first property that they talk about on page 8. If two parallel lines are cut by a transversal, then each pair of corresponding angles is congruent. Well, what's a corresponding angle? Well, let's just look at this angle right here. That angle is made between the transversal and that first parallel line. Since that bottom parallel or bottom line is parallel to the other one, then this angle must also equal that first one. When you have two parallel lines in a transversal, there's actually 4 pairs of corresponding angles that you can talk about. I've just put angle marks there next to one of those pairs. That second property there says that when you have a relationship like this with a transversal and two parallel lines, the alternate interior angles are congruent. So what do we mean there? Well, we're talking about this would be an interior angle here. The alternate one would not be the red one at the bottom. It would be alternate, like on the alternate side of that transversal. Those two are congruent to each other. And then the third property is that alternate exterior angles are congruent. So the top left one there and the top right one, those are exterior angles. I drew that green angle there. This is its alternate exterior, the one that I just drew. Now I put those angle marks in green because vertical or opposite angles are congruent to each other as well, right? So that's why both of those angles I drew in green. We can use tick marks to represent similar angles, or we can use what I'll do here is use similar colors. That means that this one and this one are the same as well, and then their vertical or opposite angles, they're congruent to each other. That's always the case when you have intersecting lines or line segments. Vertical angles are equal. So those are some good angle relationships to remember about transversals. Now let's talk about lengths. And there's some proportional things when you have 3 or more parallel lines and 2 or more transversals. Now we have a relationship like that. It just happens that the parallel lines, they cut those transversals into segments or line segments that are proportional to each other. And we'll talk about that more in lesson 8, but for right now, just understand that that top segment on the left of 6 is proportional to the segment, that ratio of 6 over 7, the top left one to the top right one, that's proportional to the bottom left and the bottom right two segments, 7 over x. Remember, proportional, that means equal ratios. That just is a property of parallel lines when they cut through transversals. the pairs of segments are proportional to each other. And we could just figure out what length x is by cross multiplying. 6x equals 49. So x is equal to 49 over 6. We'll just leave it like that. An important rule to remember: when two transversals pass through three or more parallel lines, the sides, the segments that are made of those transversals, those are proportional to each other. And usually we set up our fractions as the left side over the right side, left side over the right side, or you could do right over the left, right over the left, either way. Just keep them in order. Let's go on to part G now, and this is talking about area. And most importantly, the main thing to focus on is area of sectors in this section. And just a little bit of a review on area. If you had a rectangle with a side of length L and a width of length W, its area would equal length times width. If you had a triangle, and let's just say that was a right triangle there, and this side was length B, we'll call that, usually we call that bottom side the base when we're talking about a triangle, and we'll call that the height H, the height perpendicular to the base. The area is equal to 1/2 times the base times the height of the triangle, the height perpendicular to the base, right? Now a circle, all we need to know to figure out the area of a circle is its radius. Remember, the radius is equal to pi times, or the area is equal to pi times the radius squared. That's how we figure out the area for a circle. Pi r squared. Remember, pi, that's about 3.14. We've known about circles for a long time. The Egyptians, they used 3.16 for pi. Solomon used around 3 for his value for pi, and he did that when he was building the temple. You can find that in 1 Kings 7, chapter 7, verse 23. Now, a sector, what that is, let's just draw a little bit bigger circle. Best way to think about a sector is just like a slice of pizza. Think about that as a pizza, and there's a sector or section, a slice of that pizza. The way we figure out the area of that sector, I'll just shade it in so you know exactly what I'm talking about there. That shaded in section there is to figure out this angle that is bound by those two radii, this angle right there. If you know what that angle measure is, let's just call it angle X for right now. We'll call that angle X. And you know that if you go around a circle one time, how many degrees is that? 360, right? If you go around one time, that's 360 degrees. So basically what we're dealing with there is a fraction of the whole circle. That's how we figure out the area of a sector. And I'll just write down here A subscript S for sector is equal to that angle measure X divided by 360 degrees. That's like a fraction of the circle, and we just multiply that by the area, pi r squared. So we have the pi r squared, that's the area for the whole thing. Multiply that by that fraction of the circle that we're considered with. We determine that fraction by the angle measure of the sector divided by 360 degrees, which is the angle measure for the entire circle. That's a good formula to write down in your spiral notebook that you're keeping. The area of a sector is equal to that fraction of the circle. We figure out the fraction of the circle by knowing that central angle measure for the sector. And what I would do is draw that circle in your spiral notebook with the sector and put angle X in there so you can remember, oh yeah, the way I figure out the sector is by knowing that central angle measure for the sector, divide that by 360. That gives me the fraction of the circle that I want to deal with. Okay, one more section, and this one is dealing with some of the questions that you might see if you're going to take the SAT or the ACT test. These are called quantitative comparison problems, and that's kind of self-explanatory there. You're going to be comparing quantities, and on the SAT test, these are multiple choice questions, and what you do, they give you two quantities, two relationships basically that you can quantify. That means apply a numerical value to. And if quantity A is greater, you circle A for your answer. If quantity B is greater, you circle B. If they're equal to each other, you circle C. If they didn't give you enough information to determine if A or B is the correct answer, then you put D down for your answer. Let's go ahead and do some practice problems now. And first we'll start with some concept review, quantitative comparison problems, then we'll do some other practice problems that deal with the other things we've learned in this lesson. Here's a quantitative comparison problem off of an actual SAT test. And look at that relationship there. You have those two angles, 150 degrees and X, and they want you to determine if A is greater or B is greater. Which quantity is greater? Now, you won't have your spiral notebook to bring with you on this, but hopefully you know about supplementary angles, and that's always what you should do on these problems, is think, okay, what rules and definitions can I use to help me solve this problem? I remember supplementary angles, they add up to 180 degrees, so that means X must equal 30. And it's a good idea to write information on your test paper as you're working it. So X is 30, so that means A is 30 degrees. That means A and B are the same, and so your answer would be C. That's what you would circle in on the test. Let's do another one. This one's a little more complicated. We have square S and equilateral triangle T, and we say that they have equal areas. Usually that's always what they do, is they give you some information to start with. And so you have to think about that. Think about a square and an equilateral triangle, and they have equal areas. And you're comparing a length of side S, that quantity, to a length of side T. Now you don't have any numerical values really to deal with here. So this is purely just based on shape. So think about a square. Its area is S squared, right? A triangle, and that with an equal area, that means its area, which would be base times its height divided by 2, those two things have to be equal to each other. Well, just think about this. You could even draw a square, draw an equilateral triangle for sure, and just think about that. Its bottom, base, and then its height is perpendicular to the base, right? That height there is not going to be as long as those other sides. It's equilateral, so this side is length B, and so is that one. That height won't be as long as the base B. Remember also that a triangle is basically half of a rectangular or square shape, isn't it? So if you are going to have a square of side S and an equilateral triangle T with equal areas, you can just kind of tell. You just have to understand about squares and triangles to see that a side T must be greater. And just think about it too. One side of a square times the other side, that has to equal the base times the height of the triangle perpendicular to the base divided by 2. So that tells you there also that that base must be bigger, a length of side T of the equilateral triangle. So your answer must be B here. We had to know about formulas for a square and an equilateral triangle, and also the properties of a square and an equilateral triangle in order to solve that problem. Let's do some more practice problems based on what we've just learned in this lesson. Now, the Advanced Math book doesn't have practice problems like the other Saxon books that you maybe are familiar with. I make my own practice problems, and it's super important that you do these to help you understand how to do the problems in the lessons and do the problems that you've just done. If you need more practice, do the example problems that are in the book. Look at problem C here. Find an angle such that 3 times its supplement equals 720 degrees. Every single problem that you do, you should always start with asking yourself the question, what information do I know that would help me solve this problem? That's your foundational question that you should ask. Look at the words in this problem. Any word problem, you have keywords that help you solve the problem. The question says find an angle. So we're trying to find an angle such that 3 times its supplement equals 720. So let's just think about this. Think about supplementary angles. Find this angle, we'll call it x, and then its supplement would be 180 minus x, right? If that angle, if x was 30 degrees, its supplement would be 180 minus 30, which is 150 degrees. So we have this relationship here. We know what supplementary angles are. We can use that to help us solve this problem now. Find an angle, we'll call it x, such that 3 times its supplement, so that means 3 times 180 minus x, equals, pretty obvious place to put an equal sign, 720 degrees. Well, we don't have to put the degree symbol up there. All word problems, that's how you solve them. You set up an equation, you make a rule basically to help you solve the problem. The process of making a rule is called inductive reasoning. We observe something and make a rule. We've observed this word problem here. We make that rule, and then we use our algebra rules. We use deductive reasoning to solve it. We know that we can divide both sides by the same number. It doesn't change the expression. So we end up with 180 minus x equals 240. And we could remove those parentheses. Let's apply our addition rule for algebra now. We can add x to both sides, and that x would cancel there. We could subtract 240 from both sides, and we would end up with 240 canceling on the left minus 60 on the left side equals x. Now that's kind of a strange answer. We get negative 60 for our angle there, but that's okay. That wasn't a very realistic problem because you're not going to have a negative angle in a relationship like this. Sometimes the results of mathematics give us things that we can't so readily observe. Let's do another problem. We have a circle and a triangle here in practice problem D, and let's assume that both of them have equal areas. The circle's area is equal to the triangle's area. Figure out what the height h is. Okay, well, just think about what we know here. We know that the circle and the triangle have equal area, so we could say A of circle equals area of triangle. And we're trying to figure out the height. So there's this unknown value. We always need an equation when we're solving for an unknown. So we look at what we have here, we observe, we use inductive reasoning, we make a rule based on what we observe. And we know what the area of a circle is, pi r squared, and that's equal to the area of the triangle, which would be the base of the triangle times its height divided by 2. Now this triangle, or the circle, has a radius of 3 centimeters, so r is 3. 3 times 3 would be 9, and we have 9 pi is equal to 3h over 2. We could multiply both sides by 2 over 3. That would get rid of the 3 over 2 on the right side. And so our 2's cancel there, our 3's cancel there, and we end up with 18 pi over 3, or just 6 pi. The height is 6 pi, and our units are centimeters there, so that's important that we put those units. So that was kind of a unique problem there. We had to use what we knew. That's always what we do when we're solving a problem. We think about what information do I know that could help me solve this problem, and we apply that. We made a new rule basically. The area of the circle equals the area of the triangle, and we solved for that height. We could practice problem E. I want you to solve for x on this problem. Remember your properties of transversals. Those segments that the transversals are cut into are proportional. So that means that we could write 5 over 4, looking at it from left to right, that's going to be proportional to 7 over x. And so we have 5x equals 28. X equals 28 over 5. And we can just leave it like that for our answer. Notice I put a box around the answer. That's always a good idea so that you can tell where your answer was in a problem. I think it's important to show work as well. If you mess up, you can go back and tell where your mistake is. And I give half credit if I can find a student's mistakes in a problem. I can tell what they did wrong. I'll give them half credit on the problem. If they don't show any work, I can't tell where their mistake was. They don't get any credit if they get the problem wrong. We use deductive reasoning in this problem-solving process here. We applied a rule. That's what deductive reasoning is. The rule is that when you have transversals like that, the segments are proportional to each other. Okay, well that's all for lesson 1.